Well, good morning. Welcome to this first presentation in this session. My colleague Jim Shockey and I will be talking within next hour about the automotive radar and the effort that we have at Frescale for this application in terms of the technology development, in terms of the components that will be required for that. I will cover the front end, the RF components for the automotive radar applications, and Jim will be talking more about the data processing and streaming. Okay, with that said, let me introduce myself. I am Dragan Mladenovic, and I'm the operations manager from the sensors division at Frescale. I'm in charge of developing the front-end RF components for the automotive radar. In my part of the presentation, I will be covering mostly the technology that we are employing for these products. I will discuss briefly the architectures that we are addressing or proposing for this application. Shortly along the same lines, I will show some building blocks and the structures of our components. And of course, I'm not going to take much time showing the current status and results of the samples that we already have. However, you're very welcome to talk to me after the presentation. I will be around, and I can definitely show you much more regarding this front end, where we stand, what we are planning to do. So let's have this now just as a preliminary introduction to what we currently have regarding the technology. Frescale has been known as the technology company. Historically, we were always in the front of the technology development, and that stands now as well when we talk about the automotive radar applications. What is happening is actually we observed that the gallium arsenide, which is currently used in the radar applications, probably will go through the significant changes, transition to the silicon germanium, which looks like as the most promising material for the next generation of these components. And that's exactly what we are trying to do. However, we are not developing a brand new technology, the silicon germanium process flow, to address these requirements, but rather we are using the existing process flow, existing process blocks, and adding the new module in that process flow, which would enable us to have the silicon germanium selective epitaxial stages, where we can build only those devices that require to have this heterojunction in order to achieve the high frequency 77 gigahertz capability. With that said, you can see here that we are using the 180 nanometer technology node. Originally, it was the CMOS process. To that basic process, we added modules for various analog components and devices. And finally, we added a module which gives us the selective epitaxial layer for our heterojunction. What is really important here is that we have the bi-CMOS process. In a way, that differentiates us from some other companies offering also silicon germanium, but it is mostly the bipolar process. So the differentiation that I am underlining here with the bi-CMOS is significant, because when we talk about transitioning from the gallium arsenide to the silicon germanium, that is one level of the advantages that the silicon actually brings in terms of the pricing, in terms of the processing, the volumes, However, the other main point is the integration level. And the integration of our BiCMOS process is exactly the advantage that we see with this process versus the just bipolar process. Namely, when I say BiCMOS, it means we can build not just the amplifiers or the standard analog blocks, but we can also add significant digital domain and make these devices a high-level integration devices, very capable with additional features and functions. And I will mention that a little bit later. Right now, I'm just saying we do have this technology. We have been using it because it has been developed some years ago, and this is exactly what we think brings us a significant advantage in the market space. Some of the cross-sections of our heterojunction devices are shown here, basically the history of the development. Obviously, our first demonstrated hyper-frequency devices were presented like 10 years ago. First time, at the time, it was the capability of up to Fmax 110 gigahertz, which as the time went by, we enhanced, improved, and as you can see now on the right-hand side, our current heterojunction devices are capable of the Fmax almost at 300 gigahertz. This definitely helps us in delivering a good low noise performance for the 77 gigahertz operation. Some of the characteristics and measurements from this current technology and devices, you can see characteristics showing the Fmax and Ft, as well as some correlation from the reported published data from some other manufacturers and universities. You can see that Frescale with the peak Fmax actually correlates very well and is in the top performance of this type of characteristics. Let's talk a little bit now about the architectures that we are trying to address here with this technology. Obviously, speaking generically, what is required or available out there, when we look at at different regions globally, we see various requirements, and it's probably expected because there are high-class cars, there are mid-class cars, different regions target different customers. Therefore, the requirements for the complexity of these systems also vary, and we can see that with these architectures as well. The very simple monostatic radar shown here obviously integrates as much as possible into a single device and even combines or reuses a single antenna for both transmitting out and receiving the signal. In terms of the cost, in terms of the price, this is probably the least expensive architecture. At the same time, some of the performance characteristics obviously are modest as well because of this combination and the crosstalks and the noise level and so forth. Therefore, for the higher end of these systems, there is the so-called bistatic radar, where the antennas for the transmission and receiving signals are separate, and there is a much better insulation between the signal paths. Therefore, the quality of the signal, data processing, distinguishing the targets or any other causes of the noise is much better controlled. Therefore, these systems, type of systems, have a much better performance and are also in demand by some of the customers. So talking about this type of systems and reiterating what I said at the beginning regarding our technology capability to integrate both analog and digital domain into a mixed signal monolithic devices, what we are targeting here, you can see here for the transmitter, we have the transmitter which also incorporates the PLL in that monolithic signal die. So the whole control for the VCO is within the device. Because of the digital domain, the PLL, we also have the state machine there, which brings some sophistication, or brings some features that can be programmed in, and the device can be almost standalone, functioning with the controlled ramp up, ramp down features, and so forth. Basically, it removes some of the load that the microcontrollers used to have taking care of the frequencies and ramping up and down. Therefore, this device becomes very powerful with this type of integration, and it can be customized, it can offer in advance having different those functions. Therefore, easily just through the SPI, you can request which type of ramp up, ramp down feature or mode you want, and after sending that command once to the transmitter, it will take care of it and run it in that mode. Of course, whenever you want, you send another SPI command and you switch the modes of operation. So that's on the transmitter, and I believe we will be the very first one in the industry now having this type of integration, the PLL with the transmitter that has also the MPA, the divider, and some other sensors. Let me mention a little bit the receiver side. What we are targeting obviously is multi-channel receivers, and talking about complexity of this type of systems and radars, we hear different requirements. The number of channels can go from 2 up to a dozen of channels. Either way, we are capable of doing so. The next generation of the receivers, in addition to the multi-channel capability, will bring also the integration of the ADC, the converter. So between the transmitter with the integrated PLL as the single die, the multi-channel receiver as a single die, these two components, actually two die, if you would, basically represent the whole front end for the automotive radars. This block diagram goes back to the transmitter, just emphasizing a little bit more the next level of granularity, what are the main building blocks for the transmitter. I'm sorry, this is the receiver. Basically, the LO signal, which is the local oscillator signal we are using between the transmitter and the receiver, is the 38 gigahertz, which is probably easier to handle than the 77 on the board level. So you can see the doubler and the mixer after that. This is the simplest version of the receiver. Obviously, it doesn't show the multi-channels. I'm not showing here the transmitter. Let me describe it a little bit. The transmitter has, other than what I mentioned, the PLL, the state machine, the VCO, has MPA, the power amplifier, has also the temperature sensor, which is used for the temperature compensation, because we are targeting automotive applications, and that means the full capability from minus 40 degrees up to 125 Celsius ambient temperature, right? And finally, I want to mention the power control, the output power block, which gives you actually a signal where you can control if over the lifetime, out in the field even, this device maintains its output power so that you know that over time it doesn't deteriorate, doesn't lose the power, and the signal or the targets that you are measuring is really achieving the distances that you are expecting. So this is available as well as the divider that gives you also in the application a feature where you can make sure that the frequencies that you're using, 76.5 gigahertz or 77, after being divided so many times, 1,000 times or so, we are talking about the signals in the megahertz range. So you can control those signals as well, making sure that you are in the exact frequency range that you're expecting this device to operate. In any case, there are many more details that I don't want to dive into. I'm available, though, outside after this presentation if you would like to discuss that more. And I think I will turn it over now to my colleague Jim to talk about the data signal processing.
Well, thank you, Dragan. Frescale's been in the wireless business for quite a long time, and they were involved with a lot of the early development of the SIGI-C type of technologies that are being used in these radars. That's really where the exciting stuff is happening right now, and we're bringing a lot of that innovative capabilities that we've utilized in our wireless division for a long time to this new area. And really, the SIGI radar is positioning the automotive industry for a significant step forward in the ability to put these sophisticated systems into your cars and make it cost-effective for regular people like us to buy. Or probably some of you are here are driving BMWs already anyway and are not so worried about that cost aspect. But for a lot of us, the reality of these advanced systems is about to happen largely because of these technologies that we're discussing. So my part of this presentation is really focused more on the digital side. Now that we've gotten the analog signal into the system, what do you do with that? How do you process it? For those of you who might have come to the session last year on the radar, it's very similar coverage, kind of limited to the specific signal processing that's involved. So some of this may be familiar to you. But a quick overview of the signal processing that's done in the radar system. This is in the modulation techniques that are used by the transmitters and receivers of the radar. Pulse-modulated solutions are really the original approach to radar, and they are indeed used in automotive applications today, mostly for short-range detection, pre-crash type applications, blind spot detection. They're very simple to implement, simple electronics involved with generating the pulse waveform, but it's also limited in its ability to detect range. So it makes it good for short distance type functions. Now there are some approaches that are being used. There was a paper published just last year talking about how to extend pulse radar into more sophisticated applications like adaptive cruise control. So there are some thoughts about how this can continue on and be a part of some of these more advanced systems in the future. FMCW, frequency modulated continuous wave modulation techniques, are pretty much the more common approach to addressing the advanced systems like adaptive cruise control or pre-crash. Certainly any distance tracking that's involved for an automotive situation like detection of an object out to 100 or even up to 200 meters distant at a fast enough rate to be able to start to modify the car's behavior or track the objects around the car so that you can take effective action in relation to what they're doing. It has much better range accuracy because you don't get that ambiguity that's caused by the pulse transmission. You can be continuously transmitting as opposed to a pulse form of modulation where you have to transmit and then wait for the receive form. FMCW, your transmitter is constantly broadcasting. It's shifting its frequency, though, as it broadcasts, so you're actually looking at the resulting information shifted in time somewhat, so you don't have the collision between the transmitted data or not. Now, there are also techniques using frequency shift keying. Not so common in the automotive industry that I've seen, although there are people who are talking about ways of combining some of the features of FM and pulse technologies to try to get some of the benefits of both, but retain some of the simpler electronics involved with the pulse type modulation. So what I'm showing right now is what you would see in an FMCW modulation scheme. Again, this is the one that's the most commonly used today, so this is what the focus of the rest of this discussion is going to be. When you're talking about just detecting distance, you're really looking at just recognizing the transmission time of the pulse to its receive time. Very simple. And divide by 2 and you essentially have the distance to the object that's reflecting the information. So what you see in these diagrams, and we'll start with the far left, your far left, is the simple frequency modulated waveform. This would be, in our case, around 77 gigahertz. Typically, the bandwidth that's used to transmit the frequency modulation component is determined by the amount of the distance you want to track. But typically, for our applications, it's around a megahertz that we're interested in looking at the distance on. So the blue is the transmit signal, and the red is the receive signal. So in a situation where you may have a fixed object at a distance, and all you're doing is seeing a change in distance, you would see a waveform very much like this. So we'll talk about the architecture of the receiving system here in a minute, and you'll see why this distance is significant. This shift is significant. Actually, I think I may go ahead and skip on down to that. Probably would have been better to show this slide in advance. This is an overview of what a radar system would look like. Very top level, obviously. On the right, you see the digital processing portion of it, and we have devices that are very focused on this application. And to the left, you'll see components that we would provide for some of our radar analog devices. And some of the things that Dragan was talking about, they're going to be in that dark blue area. Although this is very top level and doesn't exactly reflect what Dragan was talking about, it's kind of representative of what you might see in the system. Generally, there's some tuning control that's creating that waveform that you're seeing in the frequency modulated waveform. And that gets modulated on top of that 77 gigahertz system. So again, it's oscillating at a much lower frequency. That drives a voltage control oscillator, which feeds the resulting waveform into the transmitting section. So it's being broadcast out. One of the key factors here is you'll notice there's a F-mix signal coming off of that transmit block. That F-mix signal appears back now in the receive sections. And it's in the receive sections where the return signal is demodulated against that return signal. So we end up with some intermediate frequency being transmitted, some base frequency being transmitted between the receive channels and the A to Ds that are in the rest of the system. So when we're talking about the receive waveforms in the previous, or this next set of waveforms, you'll see why that's a significant factor. That change, that shift is what really gives us the information about the environment around the vehicle. So what you're seeing here now on the top is the waveform that's external to the system, being transmitted out to the objects that are being tracked. And the waveform at the bottom, it's a very simple straight line waveform in this case, is the intermediate frequency that's coming back between the received channels and the A to Ds. In the case of the stationary object, the reflected signal comes back and gets demodulated into a very simple waveform. So we're now just kind of looking at a little V-shaped form that's really telling us the information about the distance to the object, because that's your flight time. So a very simple equation down at the bottom would just say your transmit speed over the speed of light by 2, and you end up getting the distance to the object away from you. So, but that's just one component that we're interested in. So distance is an aspect, but acceleration of the object is another aspect that we're interested in getting. And that information would come from the Doppler shift of the object in front of you or being detected. Now this next chart is intended to kind of give an idea of what the intermediate frequency of that would look like, but it's an artificial construct, because it's impossible to have a device that's accelerating but not changing its distance. In this case, this diagram is reflective of a device that is accelerating, I think, towards you, but not changing its distance. So sorry, the intent is to communicate the concept that you see in that intermediate frequency, a straight shift off of the base. So finally, when you mix the two signals together, this is more the real world waveform that you're going to see coming back to you. So it's a combination of components. So you see a bit of a Doppler shift pushing the received signal to a little bit higher frequency, but it's also shifted in time, and not only shifted in time, but the waveforms are compressing at a little bit different rate, so it's becoming less periodic at the same rate. But now you see the intermediate frequency is reflecting two different resulting signatures. As you ramp up, you see a shift of that intermediate frequency down off of the baseline. So, and then when you see it on its down cycle, now you see a shift in the opposite direction. So that delta between those two shifts is giving you information about the Doppler shift versus the time of flight. So you're now able to take this information, put it back into this basic equation, very simplified equation, and your aggregate frequency shift is now reflective of all the information that's in those two waveforms. So now that you've got that signal back in, we do a lot of basic digital signal processing that you would expect to translate that information into something that you can start to track. So there's a significant signal processing component that occurs in the system, and then there's a significant matrix math type problem that occurs to take that information now, your signal information, and put that into something that it can figure out where an object is and take action on it. So there is an interesting schizophrenia in this application, I'll call it, because it is a mix of signal processing and control code. Traditional solutions have been put a DSP on there and then put a small processor, small micro RISC processor or something in a system and have two devices. Well, obviously it's expensive, it takes area, there are lots of issues with heat buildup in these systems in the small space. And so in the future, and what we're seeing right now is utilization of architectures that combine the best of both worlds into one solution. So all the manufacturers today are kind of looking at strategies to mix those two capabilities together. So now when we start talking about that interface between those A to Ds and the digital components of the system, there's lots of challenges at how you bring those two together. From an MCU manufacturer's perspective, putting the types of A to Ds on a single MCU is probably not very practical. So one more straightforward strategy is to provide economic means of integrating external A to Ds or external ASICs into the system so that you don't have a lot of glue logic involved with bringing the two components together, but you allow the flexibility to the customer and how he designs the system. So typical mechanisms for bringing that analog data into an MCU would be some parallel digital interface. And in fact, we have defined a parallel digital interface specific to integrating high-speed A to Ds. Alternatively, you could bring it into an external bus, and we have customers who do that, but external buses have the extra overhead of an address transaction, which is essentially not needed in this situation. So the PDI provides specific signaling to do channel control. This particular interface also provides capabilities to do frame control if you wanted to interconnect a CMOS image sensor. And we opted to add those capabilities because the analog that goes into a CMOS image sensor is very, very similar to what you would see from the digital side of a standalone A to D or an ASIC A to D. So typically in radar, people are very interested in high precision information coming back. So typically we're seeing about 12-bit A to D interests. And so our device provides the capability of supporting any particular size, 8, 10, 16, up to 16-bit data widths coming back into our device, and up to 33 megahertz of performance. Typically what you'll see from the A to D's performance receiving from the received RF channel is anywhere from 5 megahertz to 40 megahertz, and it depends on the customers. Yeah. Bit. I'm sorry. That's the data bit. It should have been a lowercase b, probably. Up to 16-bit data widths. In this case, yeah, the example is simply an 8-bit, but it could be a 16-bit. And it's 16 discrete signals, so we're not doing any multiplexing. This is a generic interface, so it would work with a number of different manufacturers, high-speed A to Ds, and CMOS image sensors. It's also very typical to have a MUX in there, and actually Dragon had indicated a MUX in his system. And we've seen customers implement that in two different modes, either an analog MUX in front of a single fast A to D, or oftentimes just a digital MUX behind several discrete analog muxes. In any case, we can take that data however you would decide to do it, and we also have channel control on our PDI that allows you to select or operate a digital MUX that might be in series with the A to Ds. The other aspect of it is once you get that data into the chip, you need to position it so that you can actually process it efficiently. So we've added in our DMAs the ability to de-interleave the incoming signal. So typically what is done is you would read samples sequentially because you want to do some positioning information, and having that data in parallel gives you an exact positioning mechanism so from all the received channels. So this particular DMA allows you the ability to build discrete buffers of interleaved data. So you would see a sample from each channel, and that's what's depicted here with the changing colored elements. So that would be some number, probably 16-bit data transfer going through the system. Our PDI actually has a capability to pack data, so it will take 16-bit elements and it will build a 64-bit wide block so you can get efficient transfers through the MCU. And our crossbar architecture that's in our MCUs is very efficiently handles those 64-bit blocks because it's 64-bit wide. And as the DMA is doing the transfer and the buffer management of these discrete buffers, the CPU is fully available for doing the signal processing component or control code component. So if you look at the basic processing tasks that are used in an adaptive cruise control implementation, for example, after the data acquisition, the first stage would be noise reduction. Very commonly, you would use like a FIR filter, a low-pass FIR filter, and you would separate the noise out. Often then, the next step would be some windowing function that would help enhance the FFT calculation that follows. It's very common to do windowing because there's an effect of leakage that occurs when you're sampling data when the data starts to become non-periodic against your sample window, you'll start to lose the energy that's represented there. So the windowing function overlays another waveform, and it allows you, when you do the final calculations of the FFT, to get a more accurate reflection of the actual source frequency. Next would be the FFTs, and we see various uses of FFTs. For short-range applications, you might see some very short, 256 point, maybe 512 point FFT functions, but as you get to the longer distances, the size of those FFTs increase typically, and so we work with systems that are 2 and 4K points of data. And then finally, after you get that information translated back from the frequency domain into the time domain, so you understand where the objects are in time and distance, you now try to figure out, so what of those responses are actually real responses in the target detection mechanism, and of those detected artifacts, which one of them actually represents an object. So there's a couple of stages in the target detection. And then finally, that would go into some tracking mechanism. Kalman filters are kind of high-end. They're actually probably not utilized so much in this particular application because they're very compute intensive, at least at this point, and very complex to implement. But we do have expertise and knowledge on Kalman filters within the organization, so we do try to understand how that gets utilized. But there are also other approaches to the tracking problem. So I'm not going to go into an FFT at this case in this discussion because it would take a little bit too much time. But basically, I'll observe that the FFTs are an iterative process. It has a very compact inner loop type function, a summation in effect, and so MAC type operations are very common in FFT calculations. So engines that are efficient in processing the FFTs, would have something that's why signal processors are ever existed, because they have very efficient MAC capabilities. But these capabilities are being rolled into MCUs, and they're being rolled into ours as well. So we have some architectures that are efficient in handling those inner product functions. And in the case of our 5500 series products, there's what we call a signal processing engine. It's essentially a SIMD architecture coprocessor. It's integrated fully into the E200 power architecture core. So we're able to do 2 MAC operations simultaneously in this core. One of the significant things, though, is that we're able to do 2 32-bit floating point MAC operations in parallel. And that's something unique in the DSP world, because DSPs typically operate on 16-bit functions. From an FFT perspective for radio, it's very common to have, well, from FFT, you're processing one of 2 types of data, either real type data or complex type data. So you're doing either some floating point type operation or 2 16-bit integer operations in parallel. So not only can we do 2 32-bit floating point operations, if you decide to stay in the 16-bit realm, this SIMD architecture manages 4 parallel 16-bit data elements in its register set, and these registers are 64-bit wide. So effectively, as opposed to maybe the more common DSPs that you would find in these applications, we're actually able now to fully process 2 data elements in the FFT calculations in parallel, as opposed to really only being able to process 1 data element at a time, even when they claim that there's a dual MAC on chip. So I was showing an FMCW waveform in the previous slide. It was very simplistic, a very triangle-shaped form. But that's not actually what's done in this application. It's really a varying ramp on each edge of those triangle shapes. And in fact, they look to get 3 different ramp shapes on the signal that's transmitted out of the radar. And they do that because it helps eliminate some of the artifacts that might appear that are really ghosts and not real objects. So you're essentially trying to get that same information coming back on all 3 legs, on 3 legs of this waveform. So in this case, you see on the far left the green, red, and blue ramp that is what we're actually utilizing. So it's an up ramp and then 2 down ramps of different rates. So when you bring that over and you go back to the equation that we were talking about earlier in the previous slide, you'll end up maybe with some signatures that lay out over time based on the different ramps that might indicate maybe slightly different distances if you're getting some kind of ghosted image. But what you do is you now take those resulting signatures and you overlay them in kind of a linear regression, and you look to see where there's a response that occurs at the same point, looking at the velocity versus range. So when you detect something where they all overlap, you can have a fairly high confidence that there really is an object there. Otherwise, you'll see some kind of non-alignment of the data. And if they don't intersect, then you can assume it's not a real object, or that it's some artifact that crept into the noise in the system that is not representative of an actual object. Okay, so that's actually the first half of that tracking algorithm, that rejection of the noise. There's one other aspect of it, and that is, so what really is an object and what are two objects? So the simplest mechanism that is used for determining objects is just kind of clustering the results and looking at how they track over time. So you'll take sequential readings and you'll look at what responses actually move at the same way, same rate. So that's where some of the more sophisticated tracking algorithms come into play, mostly matrix math driven. Coincidentally, those SIMD architectures are also very effective at matrix math calculations. So when we provide our MCUs in this space, we also provide a DSP library that includes optimized hand assembly written functions for signal processing, FFT, windowing, FIR filter functions. We also have matrix math libraries to do basic math functions, decompositions of matrices, those kind of things, efficiently on our SIMD architecture. And again, they're all written in assembly by hand. So from a customer's perspective, you don't want to be an architecture expert necessarily. You want to be an application expert. We have people who are architecture experts and can do at least the signal processing component. We don't do the entire application, but we can enable you with the tools that would help facilitate implementing these systems. In fact, we have a gentleman here, Patrick Mentor, who you can also, after this session, discuss, who's involved with our tool support and also our modeling support, working with companies like MathWorks. And the customers we work with in these advanced safety systems, they're very often using something like MathWorks to help build the system, code it there, and the software we're providing, the libraries we're providing, will integrate into the MathWorks environment so that you can have a smooth transition from the model that you're building and the code that actually ends up being run on our device. So I have talked a little bit about architectural features that Frescale offers in our MCUs that address the radar application. We do have a device that's specific to supporting radar applications, and it's known as the 5561. It's based on our ESIS family of architectures. It uses the E200 family power architecture core that's designed for embedded applications. The core itself, the definition is for an integer power architecture core. The SIMD architecture that we discussed provides floating point capabilities, and it's built right into that core. So when we talk about power architecture, traditional classic power PC architecture being 32 32-bit registers, a number of 32 bit registers. In this particular application, there are actually 32 64-bit registers, so you're able now to operate in very wide data elements. The crossbar switch and all the internal memory is constructed to support that 64-bit width. So we're transacting at each beat across the crossbar architecture, 64-bit of data. We also use on-chip flash for this fully integrated MCU, and we have some advantages having flash on-chip in that we're able to organize the flash array as 256-bit wide data widths, which is a cache line fill width. So our cache controller that's utilized on the power architecture now is able to transact with our flash a complete cache line at each transaction. It, of course, gets broken down and transmitted in 64 bits across the buffer, but in our flash control unit, there is a buffer that holds that data and manages its transmission across the crossbar architecture. Additionally, for code that's being executed in a linear fashion, we have a prefetch buffer that reads the next array of the next cache line out of the flash array for positioning for the next access from the core. So if you're doing an iterative function, that iterative function is going to be trapped in our cache near the core, so it executes at one cycle access times into the core's pipeline. And of course, when you start to move back to the linear flow after you've done the iterative DSP function, Now you're transacting the next line, which is already held in our buffer, out of the slow flash into the cache on the core side. So you get very, very fast operation of the flash. And in fact, if you look at the math, it almost works out to be SDRAM speeds, which is very fast for a flash. And then, of course, we have 192K of SRAM, which is architected specifically to handle several channels of double buffered data captured from an RF front end. So we're able now to do all the processing within this MCU that you would do for an ACC type application. Their extensions are adjuncts essentially. So yes, they're not, mnemonic effect really. They have some really strange coding, but they are executed within the power architecture's instruction flow. So the pipeline to feed that SPE engine is linear to the rest of the power architecture instructions. And compilers today, we've worked with all the compiler vendors, Greenhill, Diab, there's GCC flavors of this that have intrinsic functions that allow you to access those directly. I do remember GCC supporting some intrinsics, and I don't know if that's broadly available, but I know some work was done in that. Okay, well, you'd have to look to make sure that it's in there, but I do remember some discussion of that. For sure, Greenhill's, Diab, Code Warrior, they have the intrinsics built in. Now, the intrinsics are very complicated to utilize. They're available to you to directly code, but we also provide those DSP libraries to simplify the task, because parallelization of these tasks is not always intuitive. So for some people, it can be a little bit twisted to try to look at an FF tree and figure out how I can operate on it in parallel. And in fact, it's a proprietary paper that can be made available to customers under NDA that we have that articulates exactly how that FFT would function. I don't know. It's a very old one. It comes from our networking and controller systems group. If you get with me, I can arrange to have that paper. So this pretty much concludes the DSP portion. As I mentioned, it's kind of a reduction of what we did last year from the signal processing side, because we really wanted to get you aware of the work that's being done on the RF side, because that's very exciting to us. It opens up a whole new area of technology that we can now exploit and bring some better value to you as customers. So feel free, are there other questions that we can discuss? Okay, great. Well, yes. That's Frescale technology, top to bottom, yes. And as I mentioned, we've got a long history in wireless. Yeah. We have a long history in wireless, and the whole SIGI C stuff is, Frescale was one of the original pioneers of that types of technology, and we had actually contributed some seminal papers in that area. I know the engineers back then that were participating in some of that development. So we've got some strong capabilities. One thing that I've noticed in the industry that people really like to go out and talk about their XHBT and the frequency that they're hitting on the top end, the FMAX. We have a very good technology that's equal to all of that stuff, but Frescale is not, or Motorola has not traditionally been one to really kind of bang the drum on that. But now I think it's a great time for us to bring those capabilities out to technologies like 77 gig radar. The 5561 is qualified silicon samples, and it's going into production at the end of this year. The radar is very special, so it takes a little bit extra sophistication to deal with that, so I'd have to turn that over to Dragon. You probably even want to talk to you after this if you were that interested. Well, we'll certainly be available to answer questions if anyone would like to come up afterwards and ask questions, and you're certainly free to. I know we're the first session of the day after a concert evening, so hopefully we got you ramped up a little bit to go into the rest of the presentations today. And thank you all for coming to FTF, and I hope you enjoyed the experience here.